Hey guys, what's going on? It's Adam, the science student. Today we're going to be talking about the Carnitine Shuttle and beta oxidation. So the Carnitine Shuttle is a shuttle system or a system of proteins that allows to get long free fatty acid chains into the mitochondrial matrix. Usually free fatty acids can usually transfer to or through these membranes because they're hydrophobic, but the long free fatty acid chains are too long. The small and medium free fatty acids can skip this process and go straight to the mitochondrial matrix where beta oxidation occurs. So beta oxidation, it's going to be pretty much where we get our free fatty acids and we change them to acetyl-CoA, which we can use for energy and to create different long free fatty acid chains and whatnot. We get a lot of energy, so we get all those listed per cycle. And then we're going to need to do this cycle 7 times to make a palmitate, and we need 3 palmitates to make a triglyceride. And triglycerides are our body's number one way of storing energy. So this is happening in good times where we have a lot of calories, where we have a lot of good energy, and we're making triglycerides to store for later use for bad times. So to start, we're going to start talking about our carnitine shuttle. It is done by a lot of proteins, and it's on the outer, and this is like on the outer membrane of the outer mitochondrial membrane. So first we're going to take our long free fatty acid and make it into a fatty acyl-CoA, and this is going to cost us 2 ATPs, and that's done by the enzyme fatty acyl-CoA synthase. Then we're going to get to our outer mitochondrial membrane, which is where it will go through the carnitine acyl transferase, which is where we're going to apply or add a carnitine onto our fatty acyl-CoA. So now it's going to be fatty acyl carnitine, and in this step we're going to lose our coenzyme A. Now we're going to go through the carnitine acyl carnitine translocase, which is going to get us through the inner mitochondrial membrane. And then now we're going to go to the carnitine acyl transferase 2, and this is going to split us up again, and we're going to remove the carnitine, and we're in our mitochondrial matrix, which is where we want to be for beta oxidation. And then once we remove the carnitine, we're going to have our fatty acid acyl-CoA. So that is how we got our fatty acid acyl-CoA into our mitochondrial matrix through the carnitine shuttle. Now beta oxidation is going to occur. So beta oxidation, in the first step, we're going to create some energy. So we're going to have our FAD turn to FADH2. And we know those enzymes are going to be dehydrogenases, which I'm going to get to in a little bit. I think I missed that step, or don't write that step in, but it's premature acyl-CoA dehydrogenase is going to do that. And then we're going to create this trans-enol coenzyme A. Next step is going to put in some water, and then with this water we're going to make 3-hydroxy acyl coenzyme A with the water, and that enzyme will be a hydratase. I think I'm going to go in right now and put the enzyme for the first one. Yeah, let me do that. So I'm going to write that one in, and it gets a star because we're going to get our first energy source. And this is an indirect energy source because we're getting FAD to FADH2, and it's the acyl coenzyme A dehydrogenase, like I said before. The second one is not going to be a dehydrogenase because we don't have an indirect source of energy, so it'll be our enol coenzyme A hydratase, which is because we inputted water. And then we're going to create our 3-hydroxy acyl-CoA. And then now we're going to have another enzyme that is going to create indirect source of energy. So we know it's going to be a dehydrogenase. So if it's going to create an indirect source of energy, we know it's going to be a dehydrogenase. So we're going to have L3-hydroxy acyl-CoA dehydrogenase. And then since it's that, we know it's an indirect source of energy, so it's either FAD or NAD. So it's going to be NAD plus to NADH. NAD plus to NADH. Another form of indirect energy. Now we're going to make our keto acyl-CoA. So keto acyl CoA. And we're going to input another coenzyme A, and then this is done by alpha keto thiolase. And we're putting in a coenzyme A. Beta keto thiolase is the enzyme. And then we're going to make with this is our final portion before we make our final product, which is we're going to make two acetyl CoAs and one acyl CoA. So I make a mistake here. I'm going to erase that. So acetyl CoAs, two acetyl CoAs, and then one acyl CoA, which we're going to send back, and it's going to restart this process so we can create more energy. So two acetyl CoAs and acyl CoA. And the acyl CoA is going to go and we're going to restart the process. It's going to be reused for repeating the cycle. Because we're going to need to repeat this 7 times to get enough to make a palmitate. Because palmitate is 16 carbons, and our acetyl coenzyme A is going to be 2 carbons each. And we have 1 NADH, 1 FADH, 2 acetyl CoAs. So we're going to need to do this 7 times to create enough to make our 16 carbon palmitate. So energy made from one cycle. So our energy made from one cycle is going to be FADH, which is 2 ATPs, which is an indirect form of 2 ATPs. So if that's broken down, we get 2 ATPs from it. And then we had 1 NADH, 1 NADH, which is 3 ATPs. That FADH should be FADH2, by the way. That was my mistake. And then acetyl CoA is 12 ATPs. So that's a lot of energy. It's an indirect source of energy, but that's still a lot of energy. So we got quite a bit. We got 15, 16, 17 ATP from one cycle. Now let's say we make this into one palmitate. So one palmitate, like I said before, is going to be 16 carbons. So that means we need to run our cycle 7 times. So this is 7 times the one cycle. If we run this cycle 7 times, we're going to get 7 FADH, 7 NADH, 7 FADH2, 7 NADH, and then 8 acetyl CoAs. And then palmitate is a 16 linked lipid or free fatty acid chain that has no double bonds. And so acetyl CoA is 2 carbons, so that's how we get our 16 carbons. And look how much energy a single palmitate has 96 ATP from the acetyl CoA, 21 from NADH, and 14 from FADH2, which gets us a total of 131 ATP minus the 2 ATP used to make our CoA, coenzyme A, and that gives us 129 ATP total. So our total bundle is 129 ATP. And once again, it costs us 2 ATP to make our palmityl coenzyme A, which is just the coenzyme A process. I didn't really talk about that before, but that's just something to know. So we get 129 ATP total per palmitate. And like I said before, triglyceride is our number one way of storing energy. So triglycerides are 3 palmitates. So that's going to be a lot of energy, as you guys can imagine. And so that's going to be 129 times 3. And then plus 22, because we have a glycerol backbone, which kind of holds it all together, or attaches these palmitates. And that's going to be 409 ATPs total. So that's a lot of ATP. So cool. Thank you guys for watching. So pretty much you're getting the point here. We have to go through this... We have to go through the shuttle, the citrin shuttle, to get to our long free fatty acid chains into the inner mitochondrial matrix for beta oxidation.